Okay, continuing on with section 33.4, polarization. Electromagnetic waves are polarized if their electric field vectors are all in a single plane, called a plane of oscillation. Light waves from common sources are not polarized, that is, they are unpolarized or polarized randomly. So here what you have is you have vertically polarized light headed towards you. Okay, the electric fields are all unpolarized light headed towards you. The electric fields are pointed in all the directions in the plane. An electric field component parallel to the polarizing direction is passed or transmitted by a polarizing sheet. A component perpendicular to it is absorbed. Okay, that's the 1/2 rule. So the intensity is 1/2 I0. If the original light is initially unpolarized, the transmitted intensity is half the original intensity. And if the original light is initially polarized, the transmitted intensity depends upon the angle between the polarization direction of the original light and the polarization of the sheet. And that it goes by I equals I sub 0 cosine squared theta. This is the cosine squared rule. Okay? So this applies to when it's initially unpolarized. Okay? And I think that's about what we want to cover on that particular slide. Now, just to see about your understanding of this, this figure shows four pairs of polarizing sheets seen face on. Each pair is mounted in the path of an initially unpolarized light. The polarized direction of each sheet is indicated by these dashed lines, right? And it's referenced to either a horizontal axis or a vertical x-axis. Rank the pairs according to the fraction of the initial intensity that they pass the greatest first. Okay? I'll let you think about that for just a moment or two. But here you have this direction and this direction with a 60-degree change here, 30 degrees here. Okay? Here it's 30 degrees to the other side of this axis, and it's 60 degrees up here, right? Here it is 30 degrees with respect to this axis, and also 60 degrees to that same axis. Then you have these two right here, where it's 30 degrees here and 60 degrees there. Okay? So, if you go through these, you've got one in this direction, one in this direction, right? So in this one right here, because of that orientation, that is going to be the one which has the greatest initial intensity. Then it goes all the way down over to here, okay, where they're looking at it in this manner. And this is going to be the second most, followed by this one, and then this one right here is 0. Practical exercise number 7. This is problem number 35, where you've got the X and Y direction here, and you've got two different ones, two different polarizing sheets here. This one has a polarization angle theta equals 70 degrees, and this one right here is 90 degrees with respect to this Y-axis, right? So this is going to be all the way down to here. This one is just going to be down to about over here for that one. Okay. The intensity is 43 watts per square meter. What's the intensity of the light transmitted by the system? So here what you're going to do is it's going to be equal to, since it is starting off as unpolarized, it's going to be 1/2 that initial intensity, right? That's through the first filter. That's 43 watts per square meter divided by 2, or just 21.5. Sorry, that keeps advancing on me. Through the second filter, you have to use the second equation that I gave you. IF equals 1/2 I, the cosine squared of the difference between those two. And if you did that's 20 degrees difference there, right? And the cosine squared of that is 0.883. So you have your initial intensity. The intensity that you're going to be, is what you calculated here, is what is going to be incident on that, right? So it's 21.5 watts per square meter times this factor right here to give you 19 watts per square meter. And these are essentially, these are just equation 33-36 for this one and 33-38 for this one. And these are on page 987. Next section talks about reflection and refraction. Reflection is light coming back at you into the same medium from which it originated. Refracted means that it's gone through and is changed in some manner as it goes into a new medium. So an incident beam of light can be reflected and refracted by a horizontal water surface. You can see that here's your incident beam, and you've got some that's being reflected back off of that, and you have this down here, which is your refracted. The change here is due to the difference in refractive index between these two materials. And you can see that this angle right here is equal to this angle right here. It's a lot easier to look at it that way than trying to draw a perpendicular line here and do that sort of thing. Whereas the angle here is quite a bit different. See, this does not just continue straight on down through the water. So the ray representation of A is what you are looking at over there. Okay? And when a light ray encounters a boundary between two transparent medium, a reflected ray and a refracted ray generally appear as shown in this figure over here. The law of reflection is the following. A reflected ray lies in the plane of incidence and has an angle of reflection equal to the angle of incidence, both relative to this normal. Okay, so this theta 1 right here is going to equal theta 1 prime here when you have reflection. For the law of refraction, it's a bit different. This is going to involve the refractive index or index of refraction of these two different materials. So a refracted ray lies in the plane of incidence and has an angle of refraction theta 2 that is related to the angle of incidence by this equation right here. So N2, refractive index of this medium, and this times the sine of this angle right here is going to equal the refractive index of this medium times its angle right here. So N1 and N2, as it says here, are dimensionless and are associated with a given medium, and there's our tables of those different values. So, what are some of the things we know about these things? If N2 equals N1, then theta 2 equals theta 1, and the refraction does not bend the light beam, which continues in undeflected direction. And that's this example right here, right? This angle equals this angle, so this is a straight line when N1 equals N2. Now, if the index N2 is greater than N1, this is bent towards the normal in this direction. So that means theta 2 is going to be less than theta 1. Okay? So the refractive bends the light towards this normal. However, if this refractive index here is less than what the refractive index up here, it is bent away from the normal. Okay? So in this case, the refraction bends the light beam away, and that's shown in this one right here. Okay, so theta 2 is greater than theta 1. So let's talk about chromatic dispersion. Chromatic dispersion is an interesting phenomenon. It's what allows you to see things under the shade of a tree and so many other places where you don't have perfect light. So incident white light, and then you have reflected light, and then you have refracted light through a glass right here, right? And you can see that theta 2b, okay, or that this right here is an angle right here. So both of these right here, this is the refractive light, and this is going to be because this right here has a higher refractive index than this up here. However, up here you have glass going into air. So if you had another air coming out here, essentially this would be bent back towards the other direction, right? Now, what they show here is that red and blue, right? And blue is bent more than the red component. So passing from air to glass, the blue component ends up with a smaller angle of refraction. And then when you pass from glass to air, it ends up with a greater degree of refraction, right? So those two things are, blue is always bent more than red. It's a good rule of thumb to remember. So reflection and refraction. Let's look at the rainbow next. You've got sunlight incident upon a water droplet, right? And it can all sorts of different water droplets. And it's going to have it's going to be refracted here. It's going to be reflected back here, and then it's going to come back out here at another refraction. So there you have a refraction, a reflection, and then another refraction, right? So two refractions and reflection taking place there. And because of what we know that blue is changed more than red, so that we get a change then as well for the where the colors are going to be when you appear it down below. So if you look at it at a 42-degree angle, okay, that's the angle at which they appear. And if you, as they talk about on this particular slide, whoops, didn't mean to do that. I just wanted to drop this down some. Okay, I'll drop it down a little bit more. Okay, the separation of colors when sunlight refracts into and out of a falling raindrop leads to a primary rainbow. The anti-solar point A is on the horizon at the right, okay? And the rainbow colors appear at an angle of 42 degrees from the direction of A. Drops at 42 degrees from A in any direction can contribute to a rainbow. That's in part B there, right? The rainbow arc, when the sun is higher, thus A is lower. That occurs in part C over here, okay? And the separation of colors leading to secondary rainbow, okay? You get a secondary rainbow that has a different color orientation, you note, from the primary rainbow, okay? That's the key thing that you have to know, whether you're looking at a primary rainbow or whether you're looking at a secondary rainbow. And I think that's going to be the end of what this particular section or this particular video